All right, everyone can get your starter notebook open for our Introduction to Network Science. And you look and see which modules are already set up here for you. The one we needed you to install ahead of time was the NetworkX as NX. And then we're going to make a couple plots. We are going to work with taking the graph into a data frame. So you do need pandas, and then we just throw a NumPy in there just for good luck. And we'll want our plots in line for this, so make sure you call that first. All right, I've called my cell. Now, there are some built-in data sets into the NetworkX module, so we're going to work with one of those to start out with, and we'll just call it G for graph. And we need to call the module usually if we're doing some of these functions with it. So they have a karate club, so that's the one we're going to look at. And it's spelled like this, club graph, like that. And then let's just see what a graph is. So you can see right there it's a network class of graph. And let's just see how, if we can check and see how big it is. Let's try the simplest thing first. We'll just check the length. And it looks like there are 34. 34 what though? What do you guys think that's 34 of? Okay, yep. It's probably either nodes or edges, and nodes are kind of the objects, so we'll start with that. You can access both the nodes and the edges with nodes. And that's just the basic one. So if you do that, we get what? We get a node view object. So we can't really do anything with this other than look at it right now because it's in node view. So if we want to take one of these things apart, then we actually have to convert it to a list. So let's construct that first. Let's just look and see what the first one does. That's what the comment there says. So we'll look at nodes. And actually there's a parameter that you can pass to nodes if you want to see what the attributes are. So we'll call it data equals true. And that'll give us the attributes for that node. And then remember we have to call it a list. And if we do that, that will give us back all the nodes. And if we realize there's 34 of them and we don't know what the attributes look like, that might be a lot of data to look at in your notebook. So let's just call back the first one. All right, so if we just look at the first one, looks like our nodes have one attribute, which is the club they're in. And node 0 is in club Mr. High. So maybe Mr. High is an instructor for this karate club. We're not sure yet. Have to look at the documentation. So let's do the same thing for edges. Let's look and see what edges look like. Edges, like that. And then, okay, we get the same sort of thing in edge view. It's not something we can manipulate directly. So if we want to figure out how many nodes and links there are, let's just do a list literal or a string literal. Let's go to, let's just print this out. So print, and we'll make it pretty. So let's do an F list, an F string. We'll say nodes. And then, do you remember how to call the number of nodes that we did up there before? So let's call it based on, what did we decide? Length, wasn't it? Yeah, length of g.nodes. That's our first variable there. And then let's call links. You could say links or edges, either one's fine. So let's call it links, let's put a space, and then we have g edges, like that. And then make sure you close your parentheses. All right, does anybody notice if I made a mistake here? I did, yes. So let's make sure we're calling the length and not all of the edges. All right, let's see if this gets us what we want. So it gets us 34 nodes and 78 links. So that's all these links here. It just gave us a total. Now, let's visualize it. Let's just do a basic visualization. Basically, let's just, there's a There's a network visualization module. Let's not worry about that yet. Let's just do the basic one. So we call NX, and the command is draw, the function. And we want to call G. And then we need to, because we're using matplotlib, we need to obviously show it. So if we do like that, and then I'll just call it again so get rid of that message there. All right, and that's the network we get. Now there's another parameter we can pass to it with labels equals true, which is fine for this one because they're just the labels are the nodes, and it's not going to clutter it up too much. If it were a long name, then that wouldn't really work for this visualization. But we get this here. So this is our network. So what are the things we can start looking at it, right? So you remember how many neighbors? How are they connected? So how do we calculate the number of neighbors, which is the degree? There is obviously there's a built-in function. So degree. And you have to pass in the node that you want. Okay, so the degree of node 0, let's say here, I just picked 0 because it's the first one, but it's also highly connected there, it looks like. So if we want to say, if you pass in, you get the degree of one node. That's what that function gives you. So they've got 16 neighbors. So if you wanted to find out who the neighbors are, there's another built-in, g.neighbors of 0. And what does that give us? That gives us the same sort of thing that we get from a lot of these functions. It gives us an iterator. So if we want to see what they actually are, we need to convert that to a list. So let's convert that to a list. And now it tells you all the nodes that 0 is connected to, all 16 of them here. And we want to know is that a lot or is that not very many? I mean, we can kind of look at this, but we don't know if they're the most or somewhere in the middle. So to calculate the degree distribution, there's a couple ways to do it. So just the most straightforward one is to make a list and then use a for statement to collect all the degrees and put them in one list. So for node in nodes, degree, and then put it in the list, append it, the degree of that node. And then let's look at the first few of them. So let's look at the first part of degree list. Degree, you know what, let me call it degrees because it's more than one and it's not the function. So we'll just do that for now. Degrees, let's just look at the beginning of the list. First 5 items. And so you can see that 0's got 16 and they're all less than that of these first 5. So maybe the rest are like that, maybe they're not. There's a quicker way to do this through a list comprehension. If you guys can guess what that is, start writing it, and then you can check and see if I wrote the same thing. So degrees equals degree in for n and g nodes like that. And then let's call the first part of it again. Okay, is that what you guys get? All right, it's pretty straightforward. And we get the exact same list again. Now, it's typical in network analysis to look at the degree distribution. So let's do that. Let's just plot a histogram with matplotlib. Okay, and then we'll show that. And it looks like most people have between 1 and maybe 5 connections there. And there's a couple, looks like you can see it's the 2 there, so at least 2 of them have around 16. Now, you don't always want to have to do a list comprehension for getting your degree distribution. So what we can do is, if you remember from the notes, the lesson, we had degree centrality. So let's grab that. There's a built-in function for that. And we'll just call it degree cent for now. And the function is degree centrality of the network G. And then while we're at it, let's print out a nice little string for node 0. And let's tell it that node 0 has whatever degree centrality. So let's start with print f node 0 has G degree. So we'll put out the number of degrees and then call it neighbors. And then we'll print, when we print the degree centrality, degree cent. We need the first item from that list. And it's kind of a long number, I believe, so let's just shorten it just a little bit there. And then degree centrality. Okay, does that look all right? Okay, let's try that then. Okay, node 0 has 16 neighbors and 0.48 degree centrality. All right, now who can tell me again what that means? What does 0.48 represent? Yep, it's the percentage. So we're basically saying that node 0 is connected to 48% of the other nodes. And there's 16 of them that he's connected to. So we're not sure if that's the most, but it looks like it's either the most or the second most maybe. So let's grab let's replot the degree centrality and see what it looks like compared to the degree distribution. You guys have any guesses about how they're going to compare? Yeah, so let's look at it. Degree, remember we got to pass it into a list, right? Cent, and because it's in a dictionary, did we look at that? Okay, well it is. Let me, I don't want to spoil it because we're going to look and find the most value later, so we'll just, do you guys remember how to call the values from a dictionary? Yeah, values, right? Okay, and then we need to show the plot again. And voila. It's the exact same distribution, which makes sense if you remember. It's just the normalized degree distribution. So this is degree centrality. And if you remember, the most was 48 there, or node 0 had 48. So it looks like there's 2 over here again, and the rest of the graph is the same. So we use degree centrality because sometimes it's more than 34 nodes, maybe it's 34,000 nodes, and if we can put it on a 0 to 1, then we can analyze them all that way. Now, remember, let's find the shortest path. What's the fastest way? So if we go back, let me show the graph again so we can see who might want to meet who. So if let me just go back up here and grab this code. All right, so because we just want the same graph again. Sorry for the scrolling. All right. Now, if you notice something here, does this look like the graph we had before? Let me scroll back real quick and show you. Most it looks like 33 is kind of over here and 0 is over here, and it looks like the biggest cluster is to the left side, right? Now, if you go down here, looks like 33 is way over here and 0 is down here. So the thing with drawing this is it doesn't draw it the same every time. And if you want it to be a more predictive or predictable output, then you will probably want to use the other module that we're not going to look at today. But we'll get to it next lesson. So let's say 16. Where was 16? Okay, oh, here's 16 down here. So what's the other end of 16? 33. So if 33 looks like it's really well connected, but 16 is already close to 0, how far away is 16 from 33? Now, obviously, you want to check, are they already connected? It doesn't look like it, but if it were a much bigger network, then we might not be able to tell. So the way that you can check, are they already connected, is the built-in function has edge. All right, so let's do 16 and 33, and we get a false back. So they're not connected. That's a good way to check that. So what's the shortest path between them? There's another built-in function, shortest path. And we're going to pass in the graph that we need and the two nodes that we want to check. So 16 and 33. And it's going to give us back the actual path. So 16 should go to 5, you should go to 0, you should go to 8, you should go to 33. Now, is there another way to get there? Sure, because it looks like 6 is also connected to 0, right? So there's probably a bunch of shortest paths because 0 and 33 looks like they're not directly connected, but a whole bunch of people are connected between them. So let's see if we can just find how many there are, because I don't think we necessarily want to print out all the shortest paths, but if we can figure out at least how many there are. So let's go back and build on it. So NX, actually I'll just copy this up here. So we want to start with that at least. Actually, you know what? We don't, because we don't want just one shortest path. So there's another built-in function, NX all shortest paths. Again, we pass in G1633. Okay, and that's going to give us all the paths, and we don't necessarily want all the paths, right? We just want to know how many there are. So like most things, we have to pass it into a list, and then we just want the length of that list. So when we do that, we find out there are 8 ways. So there's 8 ways for 16 to get to 33. Probably most of them pass through 0. So if he's already got a relationship, if he doesn't have a relationship, he needs to get a relationship with 0, and then 33 will be much easier to get to. Or you could just make a relationship with 8, but you don't know how many other people that's going to build his network up for. So let's move on to the next thing. Who knows the most people? Is it 0 or is it somebody else? So if you recall, the degree centrality is a dictionary with the nodes as the keys and the degree centrality as the values. So let's just do this and check and see what the maximum value is. Degree cent of the values. And so there's actually, if you remember before, node 0 had 48, and this one's got 51. So there's somebody in this network that has a 51 degree centrality. So let's see if we can figure out who that node is. Now this is not a real intuitive way to do this, and I'm going to show you a better way for a larger network, but this is just a little hack way that works fine. So we need to find the degree centrality, but it's going to look through the nodes and we want the key. So this works, but I don't know why. I just found it on Stack Overflow, degree cent, and we want to get the key. The key is something that we go get. I don't know why that works. It's a quick way that you can use if you're just doing it once, like we will here. So turns out node 33 is the one. Now if you want to get them together, which kind of makes sense too, then we need to use our zip function and then put those two things together. So it'll search on the first thing in these two values, because we want the highest value, we don't want the highest node. And then we want to match it up with the key from there. So if we do that, we'll do this. Now just to show you, this doesn't work if we don't put them in this order, because it'll search on the first thing. So let me show you it not working. So max zip because it makes more sense to put the node first, but if you try to do that, you'll get the highest node, which is, let's see here. Oh, let me just do the minimum. I think it makes more sense because 33 might be the highest and but let me just do degree cent keys, and then dig cent values, and I think that should give us what? Okay, so it finds the lowest node, right? And then you know that 48 is not the lowest degree centrality, right? Because 48 and 51 are the two highest values. So I'm just showing you that order matters if you're going to look for it that way. So what I'd recommend you do is convert it into a data frame, but be aware that there's different ways to do the data frame. And so when they updated to NetworkX 2, they took out the most obvious thing that you might try to use is 2 pandas data frame. And the reason for that is because a network is not just a data frame. It's more like a relational database. So if you're going to make one big flat table out of it, you have to know which part of it that you're going to flatten. And we'll talk about some of the other ways to do this next time, but we're just going to do, let's take the nodes out and then add our degree centrality in there so we can sort it. So let's just call it k nodes. For karate nodes, let's call a data frame. So PD data frame. And now what do we need to do? We need to get the nodes out. So nx dot, and if you remember before, if we just put the nodes in here, we're going to get just the nodes. But if we want the data that comes along with it, there's a built-in function called get node attributes. And then you need to tell it which of the attributes you want. So we know that club is the attribute for, and then we pass that in. That gives us a dictionary, so we want the items from it. And building a data frame, let's go ahead and just make it pretty to start with. So let's give it some columns. And we know that we're going to have we need to pass it as a list. We have our node and our club. And we don't necessarily want a separate index after that. So let's reset the index, set index to node, and that'll clear out an extra index it would have given us. So let's see what we get when we, let me just put this down here. Let's do k nodes head. Okay, so it looks like all the first 5 are in club Mr. High. All right, so if we wanted to add the degree of centrality that we created earlier, we need to do karate nodes. If you guys remember how to add a column to the data frame, yep, we can just name the column and then set it equal to the series there. So degree, or the list in this case, and we want the values. Okay, and then let's do the head again. And you can see there we've added the degree centrality. Now, this is all in a data frame, and this is just the head. So now we can do things like .info, and we've got 34 entries. Personally, I like looking at the other one better, so let's just go back to that. All right. Now, how many clubs are there? So we're seeing all these Mr. High here. Let's see if we can do a couple more analysis before we close this out. So k nodes, and then which column we're doing? Club. And how do we find out? How many clubs are there? A couple different ways. We'll just do value counts. So you can find out if everybody's in Mr. High and there's only a couple others. But no, it looks like there's only 2 and they're half and half. So whoever officer is has half the club and Mr. High is the other club. So let's find out who are the 5 most popular people or nodes. So any guesses how we do that? Yep. This is just our straight panda stuff, right? So K nodes sort values. And we want to sort on what? Degreescent, right? And if we're going to sort them, we want the most popular, right? So what else do we need to pass? Right, ascending is false. Equals false. And we only want the top 5, so what else? We can do head. And we find out that Mr. Officer, or node number 33 in the Officer Club, is the one that's 51 that we found before 33. So node 0 is the 48, and then it kind of goes down from there. So those are the first things that we were going to do with graphs. Now you guys are going to break up into pairs and work on the next exercise, and we'll be walking around coming to help you guys out if you have any questions.